Welcome to this presentation on genetic algorithms for symbolic regression. Today, we'll explore how these powerful algorithms discover mathematical relationships in data, through two practical examples. First, we'll examine a business case involving sales prediction for a sunglasses company. Then, we'll explore a medical application that optimizes personalized treatment plans. We have historical data tracking monthly unit sales alongside two potential influencing factors: social media references, and advertising budget. Symbolic regression is a type of machine learning that searches for mathematical formulas to describe relationships in data. It is based on the genetic algorithms AI tool. Unlike neural networks, symbolic regression discovers interpretable formulas that can be enhanced with domain expertise and heuristics, creating models that blend computational discovery with human knowledge to prevent unrealistic predictions. In our analysis, we're working with three sets of time series data, obtained over the last 12 months. The first one is the number of units sold, which is our target variable. The second is the amount of social media references, a potential source variable. The third data series is our advertising budget, another potential source variable. The question is, can we find a formula that explains how these source variables influence our target variable? Looking at our graphs, we can observe some patterns. There seems to be a relationship between social media references and unit sales, but it's not immediately obvious what mathematical formula might connect them. Similarly, advertising budget shows a spike early in the year, but its effect on sales isn't easy to determine. Finding the right mathematical formula is challenging. Should we use addition, multiplication, or more complex operations? What coefficients should we use? Traditional methods require us to guess the structure, but AI's genetic algorithms can discover the rest for us. In our genetic algorithm approach, we represent potential solutions as chromosomes. Each chromosome encodes a formula with the following coefficients k1 to k5. The exponents, n1 to n5. The four operators, op1 to op4. And the time lag to account for delayed effects. The number of formula terms, which is 5 in this example, is normally chosen based on the complexity and structure of the training data. The genetic algorithm can also be set up so that it will consider logarithmic, exponential, and trigonometric operators. However, using the four basic operators is usually the preferred first choice, to minimize numerical problems down the road. To evaluate how good a formula is, we use a fitness function. This measures the total absolute error between the predicted sales from our formula and the actual historical sales data. The lower the error, the better the formula. The algorithm starts by creating a population of random formulas. Each formula has random coefficients, exponents, and operators. Most of these will perform poorly, but some might contain useful patterns. Through a tournament selection process, we identify the most promising formulas in each generation. These formulas have the lowest error when predicting historical sales data. These selected formulas then undergo crossover, combining elements from two parent formulas to create offsprings. This mimics biological reproduction, where genetic material from two parents combines to form new individuals. Occasionally, just as in nature, random mutations are added to the formulas, changing coefficients, exponents, or operators. This helps explore new solution spaces and prevents getting stuck in local optima. As the generations advance, we can see the fitness steadily improving. The output of the run shows the error decreasing from initial values of over 140,000, down to around 300, representing a dramatic improvement in prediction accuracy. Let us look at how our best overall formula performed. The orange line represents our formula's predictions, while the blue line shows the actual sales of last year, sales influenced by the time series data of both the advertising budget and social media interest. The close match indicates our formula has successfully captured last year's patterns in the data. The formula is shown on the screen. This complex formula would have been nearly impossible to guess through traditional methods. Looking again at the graph, we can see our formula tracks the general trend, without capturing every fluctuation, which would indicate overfitting. And it does that without missing major patterns, striking a perfect balance between the two. Now, with the learning phase over, we can use our regression formula to predict next year's sales, relative to an anticipated social media activity, and our planned advertising budget. Our forecast provides valuable business intelligence for inventory planning and sales forecasting. Now, if what we see as a result of our first analysis does not meet our expectations, we can easily modify our planned advertising campaign, or see the effect of social media interest on the sales next year, taking action where it seems most profitable. We can continue to reshape these factors until our sales profile is closer to what we would like to see. Another useful outcome of trying various combinations for our planned actions next year. Here is another example for the use of genetic algorithms symbolic regression. This time we will look at medical treatment optimization. In medicine, there are often significant differences in the way individual patients react to various therapies. Traditional approaches often rely on population averages, but what works for most might not work for a specific patient. Our goal is to develop a model that captures an individual patient's unique response to certain treatments, in a reliable and explainable manner. Let's examine our dataset for a specific patient. We have a health marker value that indicates the patient's status, ranging from 90 to 100, over a 12-month period. We have two treatment protocols, treatment A and treatment B, each represented as binary data, showing when they were administered. As in our first example, also here symbolic regression can help us find mathematical expressions. But this time we want to see how different treatments affect a patient's health, as observed through this patient's markers. Unlike neural networks that operate as black boxes, genetic algorithms perform symbolic regression by generating explicit formulas. These provide full visibility, can be easily interpreted, and can even be enhanced with additional domain knowledge. This unique ability to incorporate world truths and various heuristics is unique to this AI tool. It helps avoid unrealistic predictions, and creates instead a reliable mathematical model, combining data-driven discovery with human expertise. This is of course something the medical community can appreciate, because invaluable doctors' experience can add considerable credibility to the algorithm's behavior. Our goal is therefore to create a personalized mathematical model that precisely captures how this specific patient responds to different treatment combinations. This model can then be used to optimize future treatment plans, tailored specifically to this individual. We will be using the same code as for our previous example. The progression of the genetic algorithm is similar to what we saw in the first example, but this time performing iterations in a completely different domain. So let us look now at how our best overall formula performs graphically compared to the actual measured marker data. The red dotted line shows our model's predictions compared to the patient's actual marker values, which are the solid red line. The close match indicates our formula has successfully captured this individual's unique response to the medication regime. The formula itself is shown to the right of the graph. This complex formula would have been nearly impossible to discover through traditional methods. Having captured how this patient uniquely responded to treatments, we can now plan an optimized treatment schedule for the future. The formula allows us to simulate different treatment combinations and predict outcomes before administering them. For the next treatment cycle, we've developed an optimized plan shown on the right side of the graph for treatment A and treatment B. They are still combined, but at a different schedule compared to last year. This schedule is precisely tailored to this patient's unique response pattern, with the purpose of improving his condition next year. The dotted line extending into months 13 to 24 shows the projected health marker under this optimized treatment plan. Notice how the marker continues to improve initially, then is carefully maintained at an optimal level rather than continuing to increase as it did last year. This symbolic regression approach, which is essentially a machine learning and prediction AI method, offers several advantages over conventional methods. It captures nonlinear effects and complex interactions between treatments. It's personalized to the specific patient rather than based on population averages. It can predict outcomes for treatment combinations never before given to this patient. It provides a clear and observable mathematical basis for treatment decisions rather than trial and error. And finally, it allows for the integration of domain knowledge through augmented fitness functions, enabling physicians to incorporate medical expertise and clinical heuristics directly into the model. To sum up, genetic algorithms for symbolic regression represent a powerful AI approach to personalized medicine. By capturing the previous relationship between treatments and outcomes for an individual patient, and representing it in one fully portable mathematical formula, we can continue treating the patient using truly personalized treatment plans that optimize their health outcomes. For personalized medical prediction, no AI approach rivals symbolic regression.